Hello. Hello, everybody. Thank you for being here. My name is Mariano Naya. I'm a software engineer at Skyscanner. And today I'll talk about asynchronous programming and how it works in modern Python. Basically, the idea of this talk is to actually revisit the main milestones that have been happening in versions of Python that arrived to the current state of the art in our programming language. Basically, the idea I've been digging through some old PEPs in order to understand what had been the main cornerstones with the idea of not just exploring the API, because probably you already know that or you know how to use the functions, but maybe you're interested in knowing what's behind it or how things work, or you're curious about what's internally for it. So this is a rather long journey in terms of time, because it starts with something that came up a very long time ago with generators in the year 2001 in a very old version of Python 2.2. And the idea was back in the day to support a more efficient way of computation. Like, for instance, they were created with the idea of lazy iteration in mind. So let's say you have to process a large bunch of objects, let's say like 1 million numbers or 1 trillion numbers. And one way of doing so, you say, I can put everything into a list and then process the list. And that would work, but it will take a lot of memory. So, or the same goes for any object. So the idea was to, okay, let's provide a mechanism in Python to be able to generate only the object that I need at a given point in time and no more than that, and save a lot of memory. So the point of this is that there were, the idea is, okay, we save memory and we support like the iteration pattern, and at a point in time, the generator is going to give us the value we need for that particular moment, and it's going to suspend there. And it's going to be there until we call it again with the next value that we need. So a new keyword was introduced, the GIL, and this works like with two very simple concepts. You have any function, but if that function happens to have a GIL statement in any part of its body, it's going to be a generator function, which means that when you call it, whatever is on the body of the function is not going to run. Instead, it's going to give you a generator object. So they work like a factory. When you call it, you receive a generator that was just constructed. And then you start working with that object, advancing the element one at a time. At next point, you get the element, the generator is going to suspend there. It's going to be like frozen, waiting to be called again with the next value. And there's nothing else to produce because it got exhausted. And in that case, a stop iteration exception is raised, which is the mechanism to signal that that iteration is over. So now let's say that time after we want to support coroutines in Python. And I'm not giving like an academic or like a formal definition of coroutines, but just for the purpose of this talk, we are going to have a more pragmatic understanding of coroutines. It will be something like you're able to suspend at any point in time, but you also want to be able to resume at a later point in the program to be able to continue the execution with different values. So if we were to implement this in Python, and we start to think, okay, how can we have this working? Do we have to, let's say, start from scratch and implement it, everything on top, or is there something that we can already take advantage of? And the reason why I started with generators is because, okay, they have something that we can use for advantage, which is the point of suspension. Remember that a generator is suspended at a point in time, so the interpreter is frozen in a part of the code, and then it can be resumed later on. So this PEP came along. This says coroutine by enhanced generators, because, okay, there is something that we can take advantage of. So it's not that we have to do everything again. So let's recap how far can we go with generators, with simple. Can we suspend? Yes, actually that was the whole point of using them in the first place. But can we pass some data to the generator while it's suspended? I mean, in its simple form, like in the very basic form? No, that's not possible. What about exceptions? Can we send an exception to a generator once it's suspended to signal that something has going on in the program? No, that was not possible. So that's why the enhanced part came along, and the interface of generators needed to be extended. So more methods were added to fulfill this purpose. For instance, the same method and the throw to handle exceptions, and close do some cleanup in the coroutine or the generator, but technically that's just a particular case of throw because it just handles an exception, which is generator exit. But the most important is send because it's what changes the semantics a little bit. So now let's stop for a second in this concept because, okay, we have generators and we start to think in coroutines because we can create something that we are able to suspend and interact with at a point in time in the program. So syntactically, there are differences. There hasn't been any changes in coroutines. They still use the yield keyword as the old generators did in the very beginning. But semantically, they are different because, and I will come up with this later in a few slides, but just keep in mind that even though they're written the same and they're even technically the same thing, conceptually they are meant with completely different purposes. And this will also be an important step later. For now, let's say how we can interact with coroutines, at least in a very basic form, because we're still in a very old version of Python. This is still 2005, Python 2.5. And now yield not only produces values to the caller, but it also can get some value as a result. So now yield, for example, result is what the caller is going to get when it calls the generator or coroutine. And value, in this case the variable value, is going to be whatever was passed from the outside to the coroutine. It's going to be captured. So I prepared a small example just to illustrate this. Let's say I have a coroutine that only iterates and it's counting some steps and it's printing whatever got received. So I want to create that coroutine and start sending values just to see how this now yield works in both ways. So the first thing I do is I'll create the coroutine. It's paused for a second. Wait. So once I create it, remember, it gives me a generator object because it's like a factory. And then I call next the first time. This is an important detail because if I don't call next, I'm not able to send anything to it, or I will get a type error. This is because the next, remember that it moves the execution of the coroutine or generator up to the next yield statement, so it needs to pause there so I can send the first element. Okay, so now the program advanced up to that point where it's waiting for something, and look at that line. The one is like you can think like that line is split in two ways, and only half that statement run, the part that give me the value 0, because it yielded the first step, which is started at 0 point. So now I can start interacting with the generator, and let's say that I will send, I don't know, 100. And the second part of that statement, the one that works inwards, let's say, towards from the outside to the generator, is going to run. Now receive is going to have the value 100 because it's Harris, and then the rest of the program is going to run. So it's going to increment the step, it's going to print whatever I just sent, which is the value 100. It's going to circle back to the beginning of the loop with the last to the true statement, and then it's going to find the next yield when it's going to pause again and suspend there until I do something about it. And it yielded the step now 1, and that becomes the result of send statement. So it's similar to next. Actually, now next is a particular case of send. So calling next on a generator is like sending none. But we had the idea that it's backwards compatible, and now we have the semantics. And even if this is a deliberate, simple example just to illustrate how it works, it marks the beginning of coroutines, because now that we can suspend and interact with the coroutine, we can do some asynchronous programming. We can suspend and do some non-blocking I/O operation while signaling the program that it's waiting and there's something else that can be run. So, okay, and now if I send or if I throw an exception, you can, of course, get whatever is happening. The exception is going to be thrown at the point where the coroutine is suspended. And in this case, it's going to fail because it's not handled, but you can add as part of your logic to handle the exception, of course. So now, okay, this is great, but let's see if we can do better, because this is not entirely convenient. And what if we want to have larger programs or we want to refactor coroutines? So this PEP came along, 380, which actually now we're in Python 3, so we're getting closer to the current API. It says that syntax for delegating to a sub-generators. And this is actually quite Important because it marks like two important improvements. First, now generators can return values, which before it wasn't possible. You couldn't have a return statement inside a generator because it will be a syntax error. And now the GIL from syntax was introduced, which will explain the semantics and how both things are related. One has to do with the other. So let's say I have another simple generator or coroutine that only produces two values, and I call it the first time. I got 1, of course. Then second time I got the value 2, and then there's nothing else to produce. And remember that stop iteration was the exception that was signaling that that generator was exhausted, that there was nothing else to produce. Okay, now the same happens, but the return value comes in the exception, because exceptions are just Python objects after all, and we can set any attributes to objects because they're dynamically added. So the return value will come in the value attribute of the stop iteration exception, and that way, whoever is calling that coroutine can know what's, not only that it finished and it completed, but with which value it completed. So now we can say like GIL from, like in a very most simple form, like whenever you have an iterable, and you GIL from that iterable, and then you can do a for loop, and then GIL every element of the iterable, and that would work. But that is not the actual reason why it was introduced in Python. There was actually much better use of that. And it has to do with the two previous points. Like first, this syntax is going to allow you to chain coroutines. So remember the example I just gave when you send values or you throw exceptions to coroutine, where you can do that with multiple levels. So let's say like I have a coroutine that calls another one, that calls another one. The mechanism works the same. And now it's important to know why coroutines can return values, because I can capture the return value with this syntax into a variable. And even if it doesn't look like too big deal, it's actually quite interesting, because if you look at the syntax, it kind of resembles like a thread. Like you have something running there. It's not a thread, of course. Technically, it's not a thread. But the point is, you have something there running that you don't know which order it's going to run. You don't know how it's going to run. At some point, it's going to suspend and continue. And some point in the program, it's going to stop there, and it's going to give me a final value. And I can have that in multiple levels. So this starts to improve things quite a lot. And this marks something that we are probably more familiar with, which is we can have multiple of these, GIL them from different coroutines and do like different operations, like for instance, reading from a database or doing an HTTP request, something that is not blocking, and while the actual I/O, while the actual operation in the database is going to is taking place, the program or some part of the program can know that, and okay, say this part of the code is suspended, I can run something else in the meantime and schedule the order. So let's see this with an example. Let's say that now I have a generator that I call general that calls another generator inside of that. So it GILs from that generator. And again, it's a simple example just to illustrate the mechanism, but it works all the same with multiple levels. I mean, this works at all levels. So it just prints out a loop similar to the first example, and when one part completes, it will continue with the next one. So okay, like I create my coroutine like at the beginning, and I call next to it because I want to start sending values. And of course, I get the first one, but then I send something, and remember that I'm sending that to the first coroutine, to the general, not to one of the internals. And if you see the print message, you'll see that what was printed was the first one. The first one got that string. So what happens is I send something to general passes it to the internal coroutine, it did the processing, it printed the value, it yielded something that went back to the general, and that became the result of the send statement. So now we can have more sophisticated code. We can like refactor and have smaller coroutines with more fine-grained responsibility. And of course, if I keep iterating that, this will continue until the first one stops, and then the second one will take place. And it all works like if it were just one coroutine. I would just put all the code in in a single function. So this is actually quite convenient because actually this PEP has an example of the code you will have to write if you didn't have this functionality built in Python. So it's actually saving a lot of code and a lot of trouble as well, because there are a lot of exceptions that you have to handle, that stop iteration and with different conditions, etc. So just to recap, this syntax allows us to create even more powerful coroutines and chain many iterables all together. Well, structuring our code in a more convenient way. And with this, we can start thinking about like event loops and some objects that are going to handle coroutines. But that is not all, because there are still more things to do. I mean, even if this is a great improvement, it's not everything. Like, remember that I mentioned in the beginning that there was when we first started to think about coroutines, we wanted to have like, we built it in top of generators. We said like, okay, syntactically they're the same. They use GL, the GL statement, or GL from. So, and actually technically a coroutine is a kind of generator, but semantically they're different. So generators were created with the idea of iteration in mind and supporting the iteration pattern, while coroutines were created with the idea of asynchronous programming in mind, or suspending some part of the code, or non-preemptive computation. So those are two different use cases, or completely different computing scenarios that fall into the same technical detail, which is that down the line in Python there's a generator running there. So, and also the GL from syntax works with any iterables. Generators are iterables, but there are also other kind of iterables that are not generators, are not coroutines, for instance, strings or list. So, and you can do GL from a generator or a coroutine, and that will make sense, but syntactically nothing prevents you or stops you for writing like something like GL from a string, when you were expecting a coroutine in that place. And that would fail, and since Python is dynamically typed, you probably won't notice the error until late in the program. So a more time passed, and this was okay, we need to address these limitations, and in more modern version of Pythons, again the syntax changed. Notice that since the very beginning, in 2001, when the GL was introduced, there were no new keywords in Python, and now we're in the version of Python 3.5, and the year 2015 or 16, and new syntax is being introduced. So all that long time, there was pretty much no changes syntactically, even though there were new constructions. And the idea is, with this PEP 492, we can create coroutines with its own syntax. So when you, instead of putting def, you put async def, you're creating a native coroutines. Before, it's not just a kind of generator that has a flag in the virtual machine. Now they're in the PEP, they're called native coroutines. And instead of GL from, you would use await, and this addresses the semantic or the problems that we had in the previous examples. For instance, now it's harder to make mistakes, which is a good thing. Remember that before there was nothing preventing you from doing GL from a string when you were expecting a coroutine, but now you cannot do await a string accidentally, because it will fail. Python will throw a type error saying, okay, await only works with coroutines or iterable or awaitable objects, which are objects that implement the magic method for await. So with this syntax, now things start to look more like in the last version of Python 3.7, or even in the future version of Python. And now we can take a look, okay, at what async IO is actually doing. Because, okay, now we create our coroutines with a new syntax, and async IO is just an event loop, which is an object, is the one that comes in the standard library, but you can use any other event loop. Whatever is going to happen is like, okay, we define our coroutines, and typically our coroutines do delegate to some other third-party libraries, like for instance, let's say I use async PG to connect to the database, and do await or select or a query. And what happens is the event loop is going to call a coroutine at some point in time. It's going to run the code. Our code is going to delegate to the third-party library, which down the line is going to implement the IO At that point, when we call await, it's going to return something to the event loop, so that way it signals the event loop, and it's the way the event loop knows that that coroutine is suspended, it's waiting for the IO operation to complete. So another one will take place and will run, and the same will happen again and again and again. And at all points, the coroutine is just going to be updating the status of the event loop is going to be updating the status of the coroutine. So it's going to call send or throw respectively as it happens with the exceptions. So our coroutine can know, okay, I have to act with this value, or I have to respond to this exception, etc. So down the line, there's nothing like fundamentally new or different that is going on in Python. The idea is like, okay, technically coroutines are still some type of generators, which this is for historical and technical reasons. Remember that semantically they are different. And things that look to be like completely different or completely new or different stuff are actually more simple constructions that we have been using in Python for quite a long time. It dates for a very old time. Remember that, for instance, like every time we call await, it will call something that down the line it will end up at a GL statement, just as a way of signaling that has to suspend. So this is probably the way I wanted to show or explain the way asynchronous programming works, because it's not like perhaps understanding what's behind or demystifying what's actually Python doing every time we program asynchronously in our program. That's pretty much it. I think you enjoy, I really hope you enjoy the talk and the rest of the conference as well. Thank you very much for listening. We have 3 minutes for questions, if you have any. Nope. No questions.